Okay, so today I wanted to go a little deep dive. We already talked about displacement a little bit, but I wanted to give you guys a definite formula for it. We talked about it before. Displacement was basically how far away you end from where you begin, right? So if you walk from A over to B and then on to C later on, you actually don't care about B so much. For your displacement, what you care about is that you started at A and you ended at C. That right there is your displacement. I'm just going to call it disp for now, okay? That's your displacement. So another way of looking at it is it's really kind of a change, and whenever you see this triangle in physics, remember that means change, okay? Change in. What you actually are getting with displacement is you're changing your position, okay? And if we're going to talk about position, the way we note position in physics is actually by x, okay? X is our variable for position. We start out with some kind of a first position or a beginning position, or as we call it in physics, an initial position. X initial, all right? And we ended up with someplace over here, our end position or our last position, or in physics again, our final position. Final position, initial position. So displacement is the change between the two. Okay, so our change in position, if we actually give this some kind of a formula, here's our formula for displacement. Whenever we want to find a change, we have to find out where we ended versus where we began. Okay, so it's always the final minus the initial. And what are we looking at here? Again, our position variable, which we call x. So our equation for displacement is always actually final position minus initial position. It's the difference, right, between those two. That's your displacement. And before, if you remember, we talked about velocity. So if we had that displacement, let's say it was to here, right? That displacement happened over some amount of time. If it took 60 seconds, there you go. That was your change, your delta time. So it's actually change in time, okay? So this is actually a change in position. Displacement was our change in position, right? Or change in position over a change in time. Because we could have started not at 0, but at 10 seconds, right? Maybe we started at 0 seconds, but maybe we started at 10 seconds, and we ended at, if it was 60 seconds, right? Maybe we ended at 70 seconds at the end there, okay? So our change in time would actually be 60 seconds, okay? So it's always final minus initial. So if we get this, what we'll actually end up with for a formula for this is change in position or displacement, right? That just goes on top. So that was our final position minus our initial position. That's our displacement over our change in time, which was final time minus our initial time. And that right there is your velocity formula. Anytime you want to find velocity, that's really all you have to do, okay? Change in position divided by your change in time. Meters per second, miles per hour, whatever you've got. But again, remember, it has to have a direction. How does this get you a direction? Well, if you started at 0 and went in a negative direction, you're going to get a positive value for your change in position, okay? If you can't go negative at times, so you're always going to end up with some kind of a positive value on the bottom, okay? So you could potentially go either a negative direction or a positive direction. You can actually get, right? You can get a positive or a negative value out of this equation. So the positive or the negative value will give you your direction. I went positive, 10 meters, or I went negative 10 meters. Fair enough? So that's that. What is acceleration then? Okay, acceleration is the last real term we kind of have to deal with for all this crazy kinematic stuff or motion or movement stuff, okay? So what this is, it's a change in velocity over the change in time. I started going fast, but then I went faster at the end, right? That speed at the end, the speed up or the slow down is your acceleration, okay? So if you have a speed up, you have a positive change in your velocity, you've got a positive acceleration. If you have if you're going fast and then you stop, right? You hit the brakes in your car, you're having a slow down, you're getting a negative change in your velocity. You're getting a negative acceleration. So just like what we had here, change in velocity over change in time, okay? Well, you always have to take your final value, whatever your ending velocity is, minus whatever your initial velocity was. Final minus initial is always how we find that change, okay? And we do that over time. So time final minus time initial, okay? So if I rearrange these equations, I can actually get some kind of interesting stuff happening here. What you're going to see is that over and over again we get, our x and t in there, we get v and t in there. Acceleration, when we come up with a term for that, this little a is actually how you represent acceleration. So let's come up with some very important things next, okay? When you want to find out what your final position is, imagine you had all this information, okay? How would you actually find out what your final position was? In fact, I'm going to erase all this, and I want you to think about if you have three possible things, okay? You have three possible things affecting your final position. Actually, kind of four, because time's in there, okay? So first off, and I'm not going to call it displacement anymore, because displacement is just a change in. It's a change in our position, which we call x. We have a velocity, and we also have our acceleration, okay? So, we also have time. Those are the three things that can affect our final position. If we want to know where we end, we know how much time has gone by, right? If we're not moving, if my position is unchanging, then I have zero velocity, I have zero acceleration, my final position is equal to my initial position, x is just my final position, right? So if that's the case, simplest case, my final position would be equal to my initial position if I have no motion happening, right? Okay? So if I started, if here's 0 meters, if I started at 10 meters and I have no speed and I'm not speeding up at all, where do I end? After 60 seconds or a minute or 10 years, I'll still end up at 10 meters, okay? In that case, final position is equal to initial position. But what happens if I am speeding up? Or better yet, before we even get to that, what happens if I just have some kind of a constant speed? So I'm at 10, but I have some kind of a constant speed. I'm in my car, I'm going maybe 10 meters per second, right? Now I have, that's my velocity, okay? So now I have a velocity, and I also have time. As time goes on, I get farther and farther along, right? If you're driving 50 miles an hour, after 1 hour, you're 50 miles out. After 2 hours, you're 100 miles out. After 3 hours, you're 150 miles out. Every hour that goes by, you increase your position by 50 miles, right? You have this nice, if you've got my position versus time, if you have a consistent velocity, it looks like this. Every time I go the same rise for my given run, okay? So if that's 50 miles per hour, there's 50, after another same equal amount of run over here, I will go up by the same number, so I'll be at 100 now. After the same run again, I'll be over here at 150. It'll be a nice regular increment, okay? If I'm going 10 meters per second, after 1 second, I've gone 10 meters. After 2 seconds, I've gone 20 meters. After 3 seconds, I've gone 30 meters. I have a nice regular increase in my position over time, okay? So velocity and time together, both of those, velocity with some amount of time, right, must also be included in here. And if I think about this, let's look at my units, right? Velocity is in, let's say, meters per second. That's probably the most common way we're going to look at it. If I want to get meters out of this deal, right, I've got to multiply by seconds so that seconds will cancel out. So that means to get velocity into a position, okay, what I have to do, if I want to do that, I've got to take velocity times my velocity unit times my time unit will give me a position. Velocity times time will give you your position. So that means, over here, there's more to this final position equation. Okay, it's not just where I start, but it's also if I have a speed. Okay, so whatever position I start out with, if I also have a velocity, I have to factor that in, how fast I'm going at the beginning, and how much time has passed. Okay? But there's one other thing in here, okay? What if I'm speeding up? I start out with an initial velocity of 10 meters per second, but I have an acceleration of 1 meter per second. What does that mean? So my position, again, over time, if I had a nice constant velocity, it looks like that. But what happens if I'm speeding up? Well, that means every minute that goes by, instead of having a nice constant slope, my slope actually increases every second that goes by, and I end up with an exponential curve, okay? So that's what acceleration will look like, an exponential curve on here. Constant velocity on this kind of a position versus time graph will look like a nice straight line for a constant velocity, okay? So that's just v was constant, okay? But if velocity is constantly changing or accelerating, acceleration looks like this. And that looks like an acceleration is constant here, because you have that slope of this thing is continually changing at a regular rate as you go, okay? It's kind of weird. But you can now imagine, okay, if I'm accelerating, well, in the first second, I didn't accelerate at all, okay? So in the first second, I went 10 meters per second, but instantly in the next second, I went 11 meters per second, right? And I didn't accelerate for that period, okay? So now I went 11 meters for that second, right? I went slightly further, I went 1 meter further for that second, okay? And then the next one, if I'm accelerating by 1 meter per second, right? So instantly at the end of that second, I speed up to 12 meters per second, and all of a sudden I'll be going 12 meters in that 1 second, okay? So my acceleration also has to factor in here. And the way that we put that in is our equation will have a 1/2 acceleration times time squared, okay? So your formula for this, let me write it in here so you can see a little better, okay? So to find out what position you actually end up at, your final position, x final, is actually equal to your final position, what position you started at, okay? How fast you were going at the beginning, times, right? Times how much time has passed. And you have to include if there's any acceleration or speeding up effect as you go along. And for how long that acceleration is going on for. Okay? So if you want to find your final position, there's actually a lot that can go into it. What happens if you don't have an acceleration? Well, guess what? If you don't have acceleration, if your acceleration is 0, you just get rid of it. You don't have to worry about it. Don't include it in your equation. What if you don't have a velocity? Well, if you don't have a velocity, then you're going to end in the exact same position you started with. All right? But if you do have a velocity, this is how you include it. If you have an acceleration, this is how you include it. And again, you can take out any of these you have. If your initial position is 0, you could just pretend that it doesn't exist. If your initial velocity is 0, you could pretend that doesn't exist. You can take and add or remove any of these things depending on what your actual values are. What about your velocity? Well, we just talked about this, right? Let's say this is our velocity versus time graph, okay? If we have a constant velocity over some amount of time, then our velocity doesn't change, does it? So if that's the case, your final velocity would just be equal to your initial velocity. Velocity over here at the end of whatever time period you're looking at looks the exact same as the velocity at the beginning. But what happens if instead of a nice constant velocity, you do actually have some kind of a change in your velocity? Maybe you started at rest at 0, right? You're in your car at the stoplight, stopped, but then you hit the accelerator. Then your velocity increases, especially if you're nice and consistent with that accelerator. If you have a constant acceleration here will look like a straight line on a velocity versus time graph, okay? No acceleration will look like a straight line across. Okay, this is constant velocity, this is constant acceleration, okay? So the other thing that you then have to figure out for your final velocity is not just how fast you were going at the beginning, but if you had any acceleration. So it turns out the way you change that is over time, if you're accelerating, right? If you're going 1 meter per second squared, every second that goes by, you're going to be going 1 more meter per second faster, right? So if you start out with an initial velocity of 0 meters per second, and you have an acceleration of 1 meter per second squared, after 1 second, you add 1 meter per second to that, right? Your final velocity is now 1 meter per second faster. After 2 seconds, right, you add another 1 meter per second to that after 2 seconds, right? However many seconds that goes on, you're adding 1 meter per second for every second that goes by, right? And that's really all that affects your velocity, okay? There's some other terms that we won't get into them because it's pretty rare to ever actually need them, okay? So that's actually your velocity formula. My final velocity is the same as my initial velocity unless I have an acceleration. And again, if you have 0 acceleration, your velocity is constant. It stays the same. This is 0, you can just take it out, okay? If you had 0 velocity to begin with, well, there you go. Your final velocity is just going to be determined by your acceleration times any time that goes by, okay? My acceleration formula in this instance is actually just really boring. There's actually another term called jerk, and then there's some other things, snap, crackle, and pop, but we're not going to get into that because you don't actually need to know that too much. Your acceleration can change. That change in acceleration can change. All these things can change, okay? But you don't have to worry about it too much, okay? So my acceleration, if all we're going to, right, is at the end, what is my acceleration? If we're not worrying about any change in it, then my final acceleration is my initial acceleration. If I have acceleration, I have acceleration, okay? So don't even worry about this formula so much, all right? We can get into jerk and some other stuff later on if you want to, but again, don't worry about it right now, okay? So if I have acceleration at all, it's whatever I start out with, okay? If I have acceleration from gravity, well, that's a constant value and it doesn't change. It was at the end whatever it was at the beginning, okay? So that's kind of how this works. And don't forget your displacement is your final position minus your initial position. Okay, that's your displacement. And don't forget, a simple way of figuring out your average velocity is basically your position over time, right? Your displacement over time. That's also kind of your velocity. This is a very simplified average velocity formula, okay? So that's kind of all I have. This equation, these two equations really, they're actually the same equation. They are extraordinarily important. How in the heck are those the same equation? You need calculus to figure that one out, okay? But this equation will get you the position of anything over any amount of time as long as you have acceleration and velocity. As long as you have those numbers, you can figure out where you're going to end up. If you're throwing something, well, instead of x, you're also going to have a y, okay? If you're going one dimension, it has everything to do with where you start, how fast you were going to begin with, and how much acceleration you had over time, all right? Good example of it right here. Last thing, and I'm going to stop because I'm getting really long in the tooth here. I know. If I have this is a constant velocity tube, right? Where do my two ball bearings here start out? Well, we're going to call it 0, right? But as time goes on, they're going to fall at a constant velocity, except for when they go through the air bubble. That's where things get weird. But from there on out, they actually go at a constant rate. And in one dimension, okay? So there you go. And the plastic ball is taking its sweet time to go through there. But again, you can see the only thing that's affecting this thing is where it started out. And since this is a constant velocity tube, how fast it can actually travel through that medium, which is oil in this case. All right? So for this thing, I'll do this again one more time, get it to the end here actually, save enough time in the video without making you guys just drool all over the place from boredom, right? Okay, so if I have a constant velocity tube, right, that means I have no acceleration. Acceleration is going to affect it not at all. Okay, the only thing that affects it is its initial position, where it started out, and the velocity it has over time. Again, except for when it goes through the bubble, there's acceleration there. Otherwise, it's just velocity of the thing times the amount of time that goes by will get you your final position. Okay? If you have acceleration involved in it, it will speed up, just like if I drop it. Okay? It starts out with 0 velocity, so in this case, I have a position which is high, right? I'm going to end up getting a negative position because it's going to fall, okay? It's going to lose height. It has no velocity at the beginning, though, does it? So you can just take that part out. So if you want to figure out where gravity is going to put something at the end, you can just figure out what the acceleration of gravity is, multiply it by time squared, times 1/2, and you'll find your final position. Okay, that's all I've got, guys. We'll talk more about it later.